This is the learning target we're going to learn about today. We're going to use our Bohr model of hydrogen. We're going to determine wavelengths that are associated with specific energy changes. So what that means is that we're going to determine wavelength and the type of radiation that's either emitted or absorbed by an electron that moves between the energy levels. So this is what's called spectroscopy. This is a method of studying these substances that we do excite with this energy, whether it's infrared or ultraviolet, or there's lots and lots of different types of spectroscopy. Now, excited atoms are going to absorb and then emit that energy. Okay, that's what it means to excite an atom. They're going to go through a series of unique energy changes, and we can use those to identify them. We know what those energy changes produce, and we can determine then what elements there are in the sample. So, for example, we use this in astronomy to determine the composition of stars. We know how hydrogen and helium and other simple elements that are in the stars look through a spectroscope, and we can use that to identify what's there. Now, we can measure this energy that's either absorbed or emitted, and what that gives us is what's called a spectrum. It's a set of wavelengths that are either emitted or absorbed by this excited atom. So the way we're going to look at this in class, we're going to do this lab, how elements burn in color. We're going to expose the atom to exciting energy. In our case, we're going to heat it. The electrons are going to jump to a higher energy level. So what we're doing is we're putting energy into this electron, and that makes it jump up to an energy level that has a higher energy level. It's kind of like giving a kid a Snickers bar. You know, they get on this little sugar high and they go high energy on you. Now, the electrons cannot hold on to that energy, all right? You know, it's like your sugar high. You come crashing right back down. So the electrons are going to give off that energy or emit that energy as they fall back down to their original energy level. So to jump to the higher energy levels, they're going to absorb energy, and then as they lose that energy, it's emitted. And we're going to measure this energy according to its wavelength. So this is on the last page of your reference packet. At the top, this is the Bohr model for hydrogen. So what we're seeing here is actually the energy level drops. So our electrons started out down here where the arrowheads are, and they absorbed energy, and they got excited, and they jumped up to where these points are. Okay, and then as they fall back down, that's where we're going to measure the energy. That's their emission spectra. So, for example, this little arrow here represents a fall from the fourth energy level to the third energy level. So N is going to stand for energy level, whereas this particular energy drop is where the electron dropped from energy level 4 to energy level 1. Now what we're going to do is we're going to follow these lines down. So I'm going to show you the rest of this. Oops. Alright, so here we go. So here where we have our 4 to 3 energy drop, we follow this line down here, and that tells us that our wavelength emitted is 1875 nanometers. This falls in the infrared part of the electromagnetic spectrum. If we look at our 4 to 1 drop, this energy emitted has a wavelength of 97 nanometers, and that falls in the ultraviolet region of the electromagnetic spectrum. Now, if we look at the bottom of your reference packet, there's the electromagnetic spectrum. Covers the whole gamut, okay, all of the ways that we know about. So we talked about this in the previous video, where our longer wavelengths are down here on the left. They have low frequency, low energy. Your shorter wavelengths are over here on the right. They have high energy and high frequency. Now for the visible light, it falls in this very, very tiny little part of the electromagnetic spectrum. That's the only part that we can actually see. We can measure all of these, and we certainly use all of these in our everyday life, but the only ones that we can see are just in this tiny, tiny little section. It only covers about 300 nanometers. So what we need to do is we need to notice here that they've made this measurement in meters down here on the bottom, but back up at the top our wavelengths are in nanometers. So the easiest way to do that is just to take your measurement down here, and we're going to ignore the times 10 to the minus 7, and we're just going to multiply this number here by 100. That's the quick and dirty way to convert from nanometers to meters on this scale, okay? Because a nanometer is 10 to the minus 9, so the easiest thing to do, like I said, is just ignore the times 10 to the minus 7 and then multiply this number by 100. So 7.0 times 10 to the minus 7 meters is the same thing as 700 nanometers. So label your reference packet so you'll remember this. Then so 6.5 times 10 to the minus 7 would be 650. Then we have 590, 570, 490, 420, and 400. So we are going to look at some elements that give off wavelengths in the visible part of the spectrum in our lab. We are also going to look more closely at our Bohr diagram. When we get it back into class, and we'll be able to read that diagram with no problem.